We are going to start the topic gravitation. In this lecture, the focus is on Newton's law of gravitation. We are going to review how Newton came up with his formula. In his own words, he said that if I have seen further, it is by standing on the shoulders of giants. So, what are some of the observations and discoveries that led Newton to come up with his formula? And also, we are going to show some simple application of his law of gravitation. So the study of the motion of stars and planets had a very long history. There are records of positions of stars and planets in the West as well as China thousands of years ago. But the more systematic and comprehensive study was carried out in Europe in the 15th and 16th century. One of the most famous person who had very good astronomical observations is this Danish physicist Tycho Brahe. So back in those days, scientific research is not supported by the government and is mostly done by the rich people who have a strong interest in science. So Tycho Brahe is very rich and is able to build an observatory in his home with some of the most advanced apparatus he could find. He's also one of the last person who relies on purely the naked eye to keep track of the position of planets instead of a telescope, right? Because after him, we have Galileo, who actually used telescopes to make even more accurate measurements. But his measurements were very accurate and comprehensive, and his assistant, Johannes Kepler, was able to make very good use of the data and summarized his observation into the three laws of planetary motion. The first one being which all planet orbits are elliptical with the sun at one of the focal point. Kepler's laws are interesting in their own right, and I encourage you to read up more if you are interested. Okay, so what was Newton's breakthrough? Right, Newton's breakthrough was that he's able to come up with the formula that relates the force to the mass of the objects as well as the distance between them. Okay, so it not just describes how planet moves, but show us why they move in such manner in terms of force. Okay, so it states that if you have 2 point masses, then the force between them is proportional to the product of their masses and inversely proportional to the square of their separation. So how did Newton came up with this formula? Right, he has got a few key insights that led him to come up with this very elegant and simple equation. The first one was Galileo's experiment. Right, he knew that if he were to drop two objects from the same height, the two objects will fall with the same acceleration. Okay, we will learn in kinematics that this acceleration is the acceleration due to gravity, right? So the force acting on the object is the gravitational force. Okay, so we label it as Fg here, that's the gravitational force. And since the acceleration is constant, right, this is g, okay, what we learn in kinematics. So Fg has to be a function of m because you want the m to be cancelled on the top and the bottom so that what you get is a constant A. So there must be an M in his formula for G. Now the second insight is the Newton's Cannon thought experiment. So he had an illustration in one of his books, okay? That's a planet with a high mountain, and on this high mountain there is a cannon. So what happens when you fire the cannonball? Okay, let's watch. Okay, the cannonball will simply fall in a projectile motion to the surface of the Earth. If you were to increase the speed of the cannonball, it will obviously fall further. But it's interesting to note that as the cannonball falls, the Earth curves away from the path of the cannon, right? Such that if you were to increase the speed even more, right, this is when the speed of the cannon is so fast that the Earth curves away from the cannon even before the cannon is able to reach the Earth. And see what is the path followed by the cannonball? It will actually follow a circular path back to the original point. So this insight led Newton to actually discover that the force, the physics behind falling objects on the surface of the Earth is the same as the physics behind the motion of the moon around the Earth. Alright, so the moon orbits the Earth. When you throw an object from the top of the mountain, the object falls to the ground. They are governed by exactly the same force of gravitation. Okay, so this motivated Newton to actually write down the R squared term, because he's able to come up with the R squared term by using accurate measurements of the distance between the Earth and the moon, as well as finding out what is the period of the moon, and hence confirm that the acceleration of the moon is indeed correct if the term is R squared in his equation. Okay, so that is actually how Newton came out with this law of universal gravitation. And there's a constant G there, it's called the universal gravitational constant. Alright. And why is it called universal gravitation? Because this equation applies not just to our everyday objects around us, like falling apples. It also applies to objects like the Earth orbiting around the Sun, as well as the Moon orbiting around the Earth. It also applies for huge objects like this Milky Way, right? This is the Milky Way. And our solar system is right at the edge of the Milky Way. So if you think about it, our solar system, that's the Sun with all the planets, is actually orbiting the center of the Milky Way. And Newton's law can also be applied as a very good approximation for this situation.